Euclidean Geometry, Rider 9. Usually I have the thought process, reminder of the thought process somewhere on the screen, but I'm afraid I'm hitting a bit of a space problem at this stage. These questions are so big that there's no space to put that on the screen. But you should be used to it by now if you've watched the rest. I mean, there are 8 previous riders, and every time there's a reminder of all the thought processes. But we'll go through them anyway. A diameter of circle ABCD. So AD is a diameter. Now I've always said don't mark in everything you can see equal on the diagram. It is just to confuse you really, because the thought processes should lead you there. But if you have a diameter, it might be worth putting in that is 90 degrees, B3 and 4, and C2 is 90 degrees by angle and semicircle, because that's something that is easy to miss otherwise. Now, where it says AD produced to meet at P and NB produced to meet at Q and that sort of thing, that we don't need. The only reason why that's there is to tell you that those are straight lines, really. But we do have AC perpendicular to NQ, which means 90 degrees, all 4 are 90, that's what it's telling you. So now, we have to prove NQ parallel to CD. I really like that sort of proof because it usually falls into place so nicely. Remember, if you're proving about lines or shapes, take and say, what if it was so? What if this is a cyclic quad? What if this is an isosceles triangle? What if this is a parallelogram? What if these lines are parallel? So, here's my question. What if NQ is parallel to CD? Aha, so there I put in the hint already. Hey, there's a nice Z for you. But you should be able to see that pretty easily, hey? M4 would have to equal C2, because they're alternate angles, parallel lines, if that is the case. So we're going to see if we can prove M4 equal to C2. So we take one of them. Remember the thought process says take one. If you're proving 2 angles equal, take one and say what is it equal to. What is M4 equal to? There we are. 90 degrees. Given. Now we say is C2 equal to 90 degrees? And of course the answer is yes, because it's an angle in the semicircle. So, to prove it, pretty straightforward. M4 is 90 degrees given. C2 is 90 degrees, angle in semicircle. Therefore, M4 equals C2. So we now have the alternate angles equal, making the lines parallel. Either you can put here alternate angles equal or converse alternate angles. Alternate angles to me is shorter. Part 2. Prove that ANCQ is a cyclic quadrilateral. So our thought process, we start and say, well, what if it is a cyclic quadrilateral? Now notice that I've put a different shape on there from what I've often done. We don't have the full quadrilateral drawn in, but that doesn't mean we have to prove it by quadrilateral properties. And it just so happens that I'm going to use angles in same segments, converse. Makes life much easier. Q1 would equal C3 and 4. So let's do that. The reason why I'm doing that is it brings in the parallel lines, in fact, right? Because that's on the parallel lines, and therefore Q1 is equal to something else. What is Q1 equal to? Q1 is equal to D2 and 3, corresponding angles with the lines parallel. Now we say, is D2 and 3 equal to C3 and 4? And if you know your theorems, you'll see pretty easily tangent, chord, angle subtended by the chord in the alternate segment. Yes, tan chord. So we can do our proof. Q1 equals D2 and 3. Corresponding angles, NQ parallel to CD. D2 and 3 equals C3 and 4. Tan chord. Therefore we have Q1 equals C3, 4. And there is our bow tie complete. So we could say, well, therefore A and CQ is cyclic, Converse, angles in same segment. Not angles in same segment. That would say in same segment, therefore angles equal. This we're saying angles equal and in the right situation, therefore same segment. Next one, prove that those triangles are similar. And I like that. I can see a common angle already. So, those are the likely angles to be equal. Remember our thought process. You don't wait for the geometry to come to you. You say, well, which angles are likely to be equal? And use color. It's very useful. Yes, P belongs to both. C1 would have to equal A2. Well, I know my theorems and I can see that straight away. Right, so P1 is common. C1 equals A2? Yes, tan chord. And D equals C1 and 2, very easy. The remaining angles are equal by angle sum triangle. So let's prove these triangles similar. 1. P is common. 2. C1 equals A2, tan chord, and D1 equals C1 and 2, angle sum triangle. So we can state the similarity. I remind you again in the correct order. P is equal to P, common. C in the one triangle is equal to A in the other one. C1 equals A2. D in the one triangle is D is equal to C in the other triangle. There we are. Angle, angle, angle. Hence, complete the statement PC squared equals. So I look at this and I say, well, I need PC, PC. So in my thought process, I say, well, have a look, PC, PC. This will give us our PC squared. So therefore, I have to write that. PC over something equals something over PC. So I need PC from this triangle. And then underneath, I need PC from the other triangle. And that's pretty straightforward because I look and I say, well, what does PC go over? First second must go over first second. This is under, so PC is under. It must go under first third, therefore first third PD. There we are. Similar triangles proven for the fuzzy marker. And it follows, therefore, PC squared equals AP times PD. Prove that BC squared is CD times NB. BC squared is CD times NB. Don't even try to look at the diagram to interpret it. You know, this is where lots of people make a mistake. They try to work it out in the diagram. I play with letters. I take that and I put it into the proportion form. Now I'm going to do vertical, horizontal. Going vertically, I get BCD and NBC. I get BCD and NBC. Have a look at these two green triangles. I need to see if they are similar. Well, I look rather looking at, don't wait for the job to come to me, and I say, well, C4 would have to equal D2. I know that's the case. Tangent chord. All right. To find B1, I say, well, what is B1 equal to? What is B1 equal to? And we look at exterior angle triangle. B1 is equal to C3 plus C4. C3 plus M4, sorry. Did you see that little trick? I'm very careless. So I had C3 plus C4. Now it's become M4. Magic's magic. So B1 equals C3 plus M4 because it's the exterior angle of triangle MBC. It's MB produced. And that means it's equal to C3 plus 90 degrees. Now we're trying to prove it equal to this one here. And have a look, we have a 90 and we have C3. C3 and a 90. So that's actually equal to C2 and 3. And finally, angle sum triangle. So our proof in those triangles. 1. C4 equals D2. Pretty straightforward, tan chord. Now a little mini proof. B1 equals C3 plus M4. So B1 equals C3 plus M4, exterior angle triangle, which is C3 plus 90 degrees, which is angle BCD, which is in fact the angle there. Finally, remaining angle N is equal to the remaining angle B2. So we have the triangles similar, stated in the correct order. Angle B equals angle C equals angle D, angle N equals angle B. Now we're trying to prove that. So we have a look and we say, well, yes, we've got a BC, we've got a BC. So we have a BC above, BC below. BC above means that we must have CD below, first, second, over first, second. We have a BC below, which is third, first, which means I need a third, first above. There it is there. And that gives us what we have to prove. Now for the real killer. This looks terrible. Terrible, terrible, terrible. And that's the one that lots of people don't even try. So I'm going to show you now how I would go about it. First of all, likely to be algebraic. So we first inspect. We say, well, do we have a BM squared? Do we have a BC squared? Yes, we do. That might be useful. Do we have an AP times DP? Yes. Do we have a CD times NB? Yes. So there we are. Why don't we just put this over this equals PC squared over BC squared? There we are. I've taken this over this equals that over that. Or in fact, the other way around. That over that equals that over that. There we are there. Now, there's a subtraction here. The only way we'll get to a subtraction involving squares is with Pythagoras' theorem. So now PC is equal to MC. So the first thing I'm going to do is I'm going to say MC squared. Now have a look at MC squared. MC squared. That's in this little right-angled triangle here. It's not the hypotenuse. BC squared will equal MC squared plus MB squared, but MC squared will equal BC squared minus BM squared. Which if you divide, we've got BC squared over BC squared, BM squared over BC squared, and that's exactly what we want. So, the proof. That is the case, proven. But PC equals MC given, therefore that equals MC squared over BC squared. Which means it's equal to that because instead of MC squared, I can write BC squared minus BM squared, Pythagoras theorem. Separating it, we get what we have to prove.